Dr. Fazira Ilyana Abdul Razak is a senior lecturer at the Department of Chemistry, Faculty of Science, UTM, one of member of GChem, UTM, and associate member of CS Nano UTM. Her expertise is in organic synthesis and computational chemistry, where her research area involves applying materials in nonlinear optics and biological activities. She is an active organizer and speaker for the computational workshop arranged locally and internationally. Her current major research is the modulation of azobenzene complex for nonlinear optics application. Okay, so her title for today is Computational Design for Molecules Interaction in Biological Activity. Okay, Dr. Fazira, the stage is yours. You may start.
Hello, Assalamualaikum.
Waalaikumsalam.
Okay, so my slide is okay. The voice is okay, right?
All right.
Okay, good.
It's all clear.
Okay, Assalamualaikum to everyone. First of all, thank you very much for this invitation from CS Nano. So for today, I have 15 minutes to talk about computational design for molecules interaction in biological activity. Okay, so a bit introduction of me, as mentioned by the MC before. So I'm a senior lecturer in UTM, Faculty of Science. All right. So before I go to my to the title, let's have a look a little bit about computational chemistry. So what computational chemistry? We know that we use it to solve the equation of a model or theory for the properties of chemical systems. So basically, we have a theory, and then you want to do simulation, and then you do experimental work after you do simulation. Okay, so in a way, you do simulation to help your experimental work, so that in future, it will help your experimental work. Okay, so computational, why I do or I emphasize on work of computational, there's a lot of benefit in doing computational. First of all, because now we are dealing with this pandemic where we cannot go face to face, or we cannot go to the lab. So this is like a sort of alternative to the wet lab. But we do know that this existed long before this pandemic. Okay, so why? Because we have this parallel computing, we have cheapest hardware nowadays, we have better software, and safer. The method is much more safer than compared when you are doing wet lab, of course. Okay, and most importantly, why? Because you can get information of molecules and reaction that is impossible for you to observe experimentally. Okay, I'll just skip this. So to design calculation in doing computational work, first thing first, you have to understand, or you need to have your aim. Okay, so what do you want to study? Okay, number two, you need to have your theoretical model progression. So you need to know your method. You need to start with the less expensive to the higher cost. Okay, it depends on the basis set that you choose, the method and everything. Okay, number three, chemical representation progression. So how do you want to do how do you want to proceed with the calculation? Okay, so of course you have to start. If you have a large system, you start with a small system first that represent the whole molecules, and you have to know if whether you want to put all of the atoms, or you just want to exclude some of the atoms. And then calculation series progression. Of course, you have to start with geometry optimization. For those who already involved in this computational chemistry, you understand this already. You know that you have to start with geometry optimization, and then you can use that optimized geometry to predict your properties. Okay, number five, sorry. So number five is environment. So it's very important to ensure that either you want to do it in gas phase or solvent phase, because whatever calculation that you want to do, you want to mimic your experimental work. Okay, so some of the experimental work, you do it in solvent phase, right? When you do your NMR, when you do your UV studies, you do it in solvent phase. So you have to know that if you do calculation in gas phase, the accuracy of your result will be different. Okay, so steps of calculation. So how to do your calculation first? Number one, you need to determine your structure. Okay, there's a lot of researchers, or there's a lot of students, or a person who are interested to do calculation. They mentioned to me that they want to do this calculation, blah blah blah. So first thing first, you need to have your structure. It's like when people say no money, no talk. Okay, so for computational, no structure, no talk. So you need to have your structure. After that, you need to do some preliminary or screening calculation. So I need to explain this because some of the students that I have monitored, they are lacking, or they skip this step number 2, where this is actually very crucial to prove that your method is actually acceptable for you to do the third step, which is to calculate the desired objective. So I will show this how we do in our work. Okay, so first example of biological activity investigation that I perform. Let's have a look at this. To study new antibacterial agents. So how do we start? So for these computational studies, we divide into 2. So we want to calculate HOMO and LUMO, which is the frontier molecular orbitals, and then these results will predict the antibacterial activities. Second step is, or second aim in computational studies, we also want to determine Lipinski's rules of 5 assessment to evaluate the ideal orally active drug molecule, right? So method that we use, the software that we use, number 1, GaussView software. We have Gaussian software, and then we use ChemDraw for professional software as well. Okay, so first step in research methodology, you need to have your structure, right? So the first step is your structure. So let's say this is my structure. So I have ligand A, B, C. Okay, and then I combine this ligand A, B, C to perform, to make complex A, complex B, and complex C. Okay, so you have to optimize each of these ligand first, and then optimize for the complexes. So the method for the ligand and the complexes is very, very different. Okay. Okay, so optimize. So optimization, first step, and then you calculate HOMO and LUMO under LAN L to DZ approach, and then you calculate the HOMO LUMO, or we call it energy gap, or you call it band gap, or you call it frontier molecular orbital. Okay, all right. Okay, so I have mentioned to you before, you need to have your screening studies. So this is the results for screening studies. Screening studies is very important because when you do a wet lab, you have a concrete result, NMR result, UV results, right? But for computational, you need to prove that your method is correct, because your method is varies from HF to DFT to semi-empirical. There's a lot of methods that you can choose. So you have to prove that the method that you choose is actually correct for your system. There's no sorry.
There is 2 minutes more left.
Okay, sorry. Okay, so this is the percentage deviation for the screening studies, where you need to screen your percentage deviation should be within 5% to say that your method is correct. Okay, next you show the antibacterial activities of the results of antibacterial activities using frontier molecular orbital, or HOMO to LUMO. From here, we determine that the one with the lowest band gap is actually will have a better antibacterial activities. Why? Because it means that it is very active. The electron can easily jump from the lower state to the higher state. So which means that these are a good potential or candidates for antibacterial activities. All right. So this is the Lipinski's rule for these 3 complexes. So these are our conclusion and recommendation. And there are other studies that we have done, similar studies as well, so like this one. Again, we calculate the band gap, and then these studies by Suhaila as well, where we're able to screen or to differentiate or to give to relate experimental and calculation for this one, where we found it has a very good agreement between computational and experimental value, which is very good. Okay, so take home notes. Before I leave, I have to tell you this. For computational, when you choose different choice of methods and basis set, your accuracy will be largely varied. Okay, and it is very important for you to know the errors that associate for each of computational approach. You have to understand why you cannot use this, why you have to use this. Okay, and you cannot always accept the numbers that the computer spits out. You as a person, as a human, need to evaluate and need to understand your results and then go back and have a look. You cannot just accept and say that, okay, this is the correct number, that I should accept it as it is. Okay, so I think that's it from me. My time is up, right?
Yes, doctor. Okay.
Okay, so
Thank you
that's
very
it from
much
me. Thank you very much.
for the informative sharing. Okay, so right now we will move on to the Q&A session for 5 minutes.
Stop screen kan?
Is there any question? Okay, there is one question from Facebook.
Have you ever encountered silver nanoparticle structure? What do you mean encountered? Meaning calculate? We have for, if you mean it's calculate, yes, we have tried few different nanoparticles calculation as well, and silver nanoparticle is one of them as well. Okay, question number 2, what factors influence the choice of basis set? Okay, it's very important question. So it depends on your structure. It depends on what you want to calculate. Okay, so let's say if your structure, you want to determine electron withdrawing or electron donating group in it, or you want to identify if whether polarizability is important in your calculation. So you need to have that specific basis set. Okay, if you have, you just want to calculate, you just want to optimize the geometry, you want to optimize the structure without any electron correlation interaction, or you don't need electron correlation interaction with it, you can go with a simple molecular mechanic. So always it depends on your structure, it depends on your objective. Okay, so that's not one specific answer for that one. Okay. What are the active sites for anti-back when you determine using homolumo calculation? Active site, when we determine homolumo calculation, normally we want to determine the conjugation system. So we want to know how effective this, you know, when you change your electron, your substituents, maybe you change from benzene, you want to change to fluoro, you want to change to chlorine. So that is the one thing that we want to we investigate. Okay, so if you change the effectiveness of electron atom to donor in the system, and conjugation, if you prolong the conjugation system, the antibacterial studies will be very different. And also if you include metal in it as well, also you will have different values. Okay.
Okay, doctor. Is there any question left? Okay. If okay, thank you, doctor, for the. Oh, another question. Oh, no, no. Okay. Thank you, doctor, for your wonderful sharing for today. Okay.
Okay, thank you.